Right now, no, sir.
Right now, you don't have the questions. Do you remember the questions? No.
No, sir.
Okay. Why not? Why don't you have the questions right now? How do you get it? It's in the form of PDF,
Yes, sir.
so it's not on your phone.
So it is, but if I open it, then I won't be able to talk to you.
No, you can keep the mic on, and then you can exit Zoom. Not exit Zoom, but the Zoom can be on the background, no? Yes, Ashma?
Yes, sir. 1 minute.
What about you, Sarah? Did you submit the assignment?
So which one?
Which one? You may have got that in your app or the website if you have registered.
I'll check.
Okay, Heshma. So you're on mute. Even if you're saying something, I don't think I can hear you. Okay. By the way, Samira, can you see this answer?
Yes, sir.
So just imagine this is isolated system, है ना? Exactly. If I answer it to be isolated system, can you guess the question?
Sir, I have the question.
Actually, you have the question. What is the question? Tell me now. You have the question now.
System in which there is no exchange of matter, work, or energy from the surrounding is called.
So is it the answer is right? Correct.
Yes, sir.
Okay. What is the next question?
In thermodynamics, a quantity whose value simply depends upon the initial and final states of the system is called.
That is a state function. Correct. What do you think, Samira?
Yes, sir.
Okay. And then the third question is?
Consider the following properties. pH,
Okay. What are the properties? pH,
surface tension, volume, entropy, EMF of a cell, boiling point.
boiling point. So you have pH. Second is surface tension. What is the third one?
Volume,
Volume. Fourth is
entropy.
entropy. So there are some terms that you guys have not heard of. Fifth one you said EMF, I guess, right?
Yes, sir.
And sixth is
Boiling point.
boiling point, है ना?
Fifth is EMF of a cell.
Of a cell. Okay. So the pH, if you take a big bucket and if you measure the pH from here or here, it will be same. So that means it is what? Intensive property. What about surface tension? Now guys, what about surface tension? Will it be intensive or extensive? Okay, surface tension you don't know? You must not have okay, fine. Surface tension abhi aapko physics mein nahi aaya, okay. But maybe it should be in the first chapter of physics. Okay, volume is extensive. Boiling point is intensive, है ना? So we know at least with the three. Can you answer with the three, Samira? Do you have any option? Do you have options?
Yes, sir.
Okay. So in the option, please check now. The first and the sixth one, it should be in intensive properties. How many options are there such that? How many options are there?
4 options.
All 4 options have 1 and 6 in intensive. Your understanding आपको आ रहा है समझ में हम क्या कहना चाह रहे हैं आपसे? इस समय
Sir, I didn't understand the options only. How can we like select? Because
okay. So I think it would be something like this, no? Intensive, or rather it will be like this. A option, intensive are 1, 2, 3, 4, and in the same option we have extensive. These are 5, 6. As a option, it is something like this: intensive, extensive. Option A. Now intensive, you have 1, 2, 3, 4, 5, and 6 in the extensive. Is it like this or like this?
the second one, sir.
Second one. Okay. So it is saying that 1, 2, 3, 4, these are intensive properties, and 5 and 6, these are extensive properties. Okay. So we have to choose an option in which the first one and the sixth one are intensive property, because we know only that question. We have not learned these terms, but still we will try from how much we know. Tell me.
So D is the option.
D is the only option. Okay. And so now to check one more thing. And is the volume as extensive property in the D option? Is volume as an extensive property?
Yes, sir.
Okay, fine. Then I think this is not right, Hishma. This will be D. This will be D. Okay, Hishma?
Okay, sir.
Okay. Now what is the last question? Fourth one. Again, it is isolated system.
A well stopper thermo flask containing some ice cubes is an example of.
So it will be isolated system, right? Because if you have thermo flask and it is stopped also, na? So you can't enter, I mean, matter cannot enter it, and neither the energy will enter it. Okay. That is the whole concept of thermos flask. Got it?
Yes, sir.
This one is fine. So just check this one here. Hishma, okay?
Okay, sir.
Okay. Fine. So how are you, Mehreen? Hello.
Good.
Mehreen, can you hear me? Walaikum Assalam. How are you?
I'm good, sir. How are you?
Okay. I'm good. I'm good. Okay. So you have rejoined, I should say. How many classes did you do earlier? You came for a few classes, no?
Actually, this is my first class. Yes, before.
Before only. I remember your name. That is why I'm asking. You did a few classes, I guess. Okay. So we are studying thermodynamics, and we are done with one class. I think this must have been relayed to you that we are done with one class. So for that, in that we just started with some terminology, thermodynamic terminology. What is happening in your school, Mehreen?
We're doing hydrocarbons.
Okay, so is thermodynamics done or it is not done?
It's not done.
It's not done. Okay. Are you free on Thursday and Tuesday and Thursdays? Tuesday and Thursday. Wait a second.
Yes, sir.
Tuesday and Thursday you're free. Okay, so on Tuesday, Thursday class now we are doing hydrocarbon. Will you like to join that batch?
Yes, sir.
Yes. Okay, so just
Yes.
let me talk with Nishkar sir. Okay, wait a second. सर ये Okay, Mehreen. So I think you should get the link for Tuesday, Thursday from Nishkar sir, but just wait for a few minutes, okay?
Okay, sir.
Okay,
So
wait.
will
I
you
will.
teach from the starting?
Hydrocarbon.
Yes, sir.
Hydrocarbon. There also hydrocarbon. We have done one class, okay? That class is uploaded, and I have started with IUPAC nomenclature, even though IUPAC nomenclature is a part of organic chemistry, some basic concepts and techniques, है ना? Yes or no? Nomenclature उसी में. But I started with nomenclature because most student had some problem with nomenclature, and I'm sending you the link for that video, that one lecture. आज आप उसको देखिए. कल से you will do the live classes. Will that work for you?
Okay, thank you, sir.
Wait a second, na. I will send you a link. Okay.
Okay.
Yes. So please maybe save it or do something. Did you receive the link, Mehreen?
Yes, sir.
Okay. So just check it, na, if you can view that or not. Yes, Mehreen.
Yes, sir. I can load it.
So you can see that. Okay, fine. Sure. Thank you. Then we will. I will meet you tomorrow. Okay. Please watch the lecture. Okay.
Thank you, sir.
Okay. Bye bye. Take care. Okay. So where did we end? We ended at thermodynamic processes. Okay. Thermodynamic processes. This is your batch only, no? Yeah, see, 15th December. Then I have to add one page for 6th December. It's a Monday. Is the screen visible to you? Yes or no?
Yes.
Yes.
Okay. So please write. We did equilibrium, na? Thermodynamic equilibrium.
Yes, sir.
Okay. Fine. Now we have seen the definition of processes. Now let me give you one example, that is of a cup which has some tea in it, and it was initially at let us say 60 degrees Celsius. It was hot. Then you kept it in your desk. Now while it was at desk, it will be interacting with the surrounding. And obviously the room temperature at that time is approximately 25 degrees Celsius. So after a while, if you look at the temperature of this tea, it will be somewhere around 25 degrees Celsius. Okay. So here there was some interaction. Okay. And see, this is state 1 and this is state 2. And what we are doing, we are not defining the volume, the pressure, or anything else, and also not even the mass of the tea. But to define the state, we need only one state variable. What is that state variable? What property of this T are we using to define the state? Temperature. Yes, Mariam, correct. Temperature. Hai na? Now, there are a few things which are constant here. For example, if I talk about the volume is constant here. Like in the process, the volume is constant. Okay. So this type of process, it has a particular name. Similarly, there will be some there will be some processes in which the pressure will be same, and we'll be keeping those same for some reasons, and those processes will have a particular name. Okay, and at some point we will learn about some processes which will have the temperature which is constant. Okay, so while the process is happening, the temperature is constant. Now that also has a particular name. So on the basis of what is constant, we have different types of processes. Types of processes. Okay. Now, first of all, right, number one, isothermal process. Isothermal process. So in this process, what is constant? Temperature is the temperature is what? The temperature is constant. Okay. So iso, what is the meaning of iso? Iso means same. Therm means temperature. Hai na? So isothermal process, it means the temperature will be constant, same temperature. Then right, adiabatic process. Now in adiabatic process, there is no exchange of heat. No exchange of heat between system and surrounding. Okay. Right, the third one, isobaric process. Okay, by the way, did you guys do the Friday class?
Yes, sir.
Yes, sir.
Acha, any problem in that?
No, sir.
No, na? Okay, so whatever was done in the theoretical class, you had the extension of that in the numerical portions, right? You just did more questions. I hope you did not have any gap in the concepts, right?
Sir, I didn't get the link only.
You did not get the link. Okay, maybe ask Nishkar sir, okay? Or what about other? Hishma, did you do the class?
Yes, sir.
Sarah, what about you?
Yes, sir.
Okay, so Samaira, you only did not receive the link. Okay, ask Nishkar sir, okay? What happened?
Yes, sir.
Please tell him. Isobaric process. In isobaric process, the pressure is constant. What about Aisha? Did you do the Friday class or no?
I did, sir.
You did it, okay. So at what time did you guys do the class? I think you had a choice of slots, no?
Yes, sir.
When did you do, Aisha?
It was 6:30, I guess, sir. We did it at 6:30 from
All of you?
Saudia's time. Me and Mariam.
To 6:30.
Acha, you and Mariam. What about Hishma?
So I took the 3 o'clock slot.
3 o'clock. Sarah?
12 p.m. Indian Standard Time.
12 p.m. Okay. Isobaric process. In isobaric process, the pressure is constant. After that, you have isochoric process. Here, the volume is constant during the process. The fifth one, which is cyclic process. So in cyclic process, the system undergoes, please write, system undergoes a series of processes. But ultimately returns to the original state. Okay, it returns to the original state. Done.
Yes, sir.
Now there are two more processes, reversible process and irreversible process. Okay. So understanding them is very important. Understanding them is very important. Okay. Please. Let us start with an example in which we have there is a container and it has a movable piston. This is a movable piston, okay? And you have two such cases. And near that you have, let us say, a bag. Near that you have a bag, okay? This bag contains sand, okay? This bag contains sand. This bag contains sand. So here also you have sand. Here also you have sand. Now what I have to do, I have to pour all the sand into the piston, okay? So this piston, it does not have here any gap. So all the sand will go and it will remain on the piston. Then what will happen? The piston will go down, yes or no? The piston will go down now, like this, correct?
Yes, sir. Yes, sir.
And the piston will go down, okay? So these are the two stages, okay? These are the two stages. This is initial. And this is the final stage that I have to achieve. And in this final stage, I have some grains. These grains are of what? These grains are of sand. Okay, please don't write, just listen, okay? Now, just listen. So I can achieve this in two different ways. I can achieve this stage in two different ways. I can pour all sand at once. Right, and the another way of doing that will be add 1 grain of sand, 1 grain of sand at a time. Yes or no? Even though the later part will be very slow, even though the second option will be very slow, but with this option also, if I use this path, then also what I can do, I can achieve this final stage. Yes or no?
Yes, sir.
Yes. Okay. Now see, if I pour all the sand at once, okay, so I'm pouring all the sand at once. Please imagine it. Okay, please imagine it. Now, while the process is going on, is there any way to reverse the process? Is there any way to reverse the process while it is happening before reaching the final stage, before reaching the final state of the system? I have lifted up the sand bag and I am pouring all the sand at once. So tell me, is there any going back? Huh, guys? Is there any going back? Yes. Okay, but only after I reach the final stage, na? Midway, can I go back? Midway? Yes, Mariam?
Sir, can put the sand back in the bag.
But that will only happen after I have reached the final stage, na? I can put the sand back. Correct. Very good. Correct. I can put, you are saying that only, na, Mariam? I can take all the sand from here, but it will be in this stage, na? Final stage. Yes or no? No? Mariam?
Sir, in middle also we can stop and put the sand back.
How you have already lifted, and once gravity has acted on the sand, how I mean, what will you do? We are pouring all the sand at once.
Okay, sir.
Got it?
Yes, sir.
Hai. So is there any going back midway during the process? No, na? So if you have that type of case, now this type of case is irreversible. process. Okay, it doesn't mean that I cannot go back to this state. It means that during the process we cannot go back. While the process is happening, we cannot go back. We have to achieve the final stage. Only then we can. हाँ, okay, फिर बाद में फिर दिमाग में याद आया कि I have to get this all the sand away from all the sand from the piston to the bag once. So during the process, we cannot revert it. Is this very clear, all of you?
Yes, sir.
है ना? Now tell me, if I am adding one sand at a time, then my steps will be very small. Okay, so I am going like this, one grain of sand at a time, and I have not reached the final stage. Now midway, I thought, no, I don't want to add that into piston. Then I can start removing, है ना? So midway, I can go back. Yes or no?
Yes, sir. Yes, sir.
That means the process is reversible. It means what? It means the process is what? Reversible. This is reversible process. This is reversible process. Okay. So maybe if you want to have this visual representation of reversible and irreversible, please draw it. Let me know if you're done. Then we can move on to the differences. Okay. So a few properties you can already see for a reversible process, that the reversible process is very slow, you know. And what I can say is it is carried out very in very small steps, carried out very slowly.
Done, sir.
Okay. Acha, one more question. If I add 1 grain of sand, okay, not 1 grain, let us add, or let us pour all the sand at once. Okay, fine. We are pouring all the sand at once. Now tell me, the pressure change will be significant or it will be negligible if I pour all the sand? The pressure, because these gas will be feeling some pressure, right? If you have some gaseous molecules here, it will be feeling some pressure right now. And if I add the whole bag of sand, the piston as it falls down, the pressure change will be significant or it will be negligible?
Significant.
Significant. Okay. And what if I add only 1 grain of sand at a time? The pressure change will be negligible. Right? It means that we have opposing forces here. Okay, we have some opposing forces. For example, if nothing is happening, see, in the initial stage, nothing is happening. In the final stage, nothing is happening. Whatever is happening, is it happening in between? We have seen that concept in the thermal equilibrium and also what processes are. In that, we saw that initial stage, nothing is happening. Final stage, nothing is happening. Now, in initial stage, if nothing is happening, it means that we have two pressures. We have a pressure of the gas, which I will call as P internal. And then there is an atmospheric pressure. Let us just call it P external here, okay? P external. Now, these two are opposing forces. They are having different directions. Now, if I have irreversible process, then the opposing force is what? It is very different, right? Like the P external will be, if I do the irreversible process, the P external will be very different than the P internal. But if I have the reversible process, in that the P external and P internal in each small steps, there may be not much different. Okay, so you can't even see if there is anything changing or not in the small stages, right? So if you can't see anything changing, then you will conclude that in all of these stages, I cannot see significant change happening. That is why I will say that all these stages are in equilibrium. In all these stages, there is an equilibrium. Okay, so this is one of the properties. Okay, let us write the reversible process and irreversible process. Let me just separate them and add a line here. Now let us write for reversible process first. So please write process whose direction can be changed at any stage. Okay, so Once again, I am emphasizing this point that the process is reversible. It is not talking about anything about the state. Okay, you're not talking anything about the state. We are just talking about the process, if the process is reversible or not. Okay, and that means can we change the direction of the process? Yes or no. Now, if I talk about irreversible process, then it will be just the opposite process whose direction cannot be changed at any stage. At any stage. Next point is the driving force. The driving force is only, now this word is very important, which I'm going to write, infinitesimally. Infinitesimally. Now, infinitesimally means infinitely small. Okay, can you see that? Infinitesimally means infinitely small. Okay. Similarly, the driving force is infinitesimally greater than, it is slightly, that means it is slightly greater than the opposing force. So whenever you have reversible, please remember to write this word. CBSE loves this word. Okay. CBSE love this word. Okay. Greater than the opposing force at all stages. Now, what will be the point here? The driving forces, the driving force is different than the opposing force. Okay, opposing force. Next one, it is carried out slowly, now very slowly. It is carried out. Now again, we will use this word infinitesimally. Slowly. Now this is, it is done rapidly. It is done rapidly. Next one, equilibrium is maintained at all stages. Equilibrium is maintained at all stages. Equilibrium is not maintained. Equilibrium is not maintained. Okay, it is an imaginary process. Okay, it does not exist. It is only imaginary. A perfectly reversible process will be imaginary. It is imaginary. And irreversible process. All the natural processes are irreversible. All natural processes are irreversible. So please write this down. So this is the last terminology that we are going to read, and from now on we are diving into the energy component. Okay, we are diving into the energy component.
Done, sir.
Done, all of you?
Yes.
sir.
Okay, now write internal energy. Internal energy. Okay, internal energy, it is shown by the letter U. Okay, So see, if you have, okay, fine. What are the energies that you know right now, except internal energy? Have you heard of any kind of energy? Have you studied any kind of energy? Lower standards? G, no.
Mechanical energy,
Mechanical energy and
kinetic energy,
kinetic energy. Okay. Anyone else? Hishma?
Potential energy.
Potential energy. Okay, fine. So you have learned some energies. Okay. Now, if you see a block of iron, do you think it has any kind of energy? If it is just resting, if it is just resting, will it have any kind of energy? What do you think? Yes or no? This is yes or no question. Tell me. If you are wrong, I'm expecting you to be wrong. Okay. So tell me, what do you think? If a iron block is just sitting there, will it have any kind of energy? It is on the ground. I'm not asking tricky questions. Yes, Mariam, tell me. Samaira? No. Samaira?
Yes.
Yes. Okay. Can you explain why? How?
Kinetic energy.
Kinetic energy. It is just sitting there on the ground. Settings. I mean, वो ऐसे ही रखा हुआ बस. So kinetic energy. What is the velocity if it is just sitting there? It will be zero, na?
Yes.
Okay, fine. Okay. So okay, it has some energy, but how you are going to explain that energy? It is internal energy, and if you see an iron block, now if you see an iron block, so it is made of different atoms. Not different atoms, same atoms, but many atoms. And even if it is a solid, I hope you know that the solid particles, they are vibrating. Yes or no? There is some motion which is happening inside this object. So even though we don't have any free energy, okay, what is free energy? Whatever it is, it does not have any free energy. It means that we cannot use the extra energy as work. Okay, we cannot get this particular iron block to do any kind of work right now. So that means we say that it does not have any free energy. Whatever energy is inside it, it cannot be used. It cannot be used. Okay, so it has some vibrational energy inside it, and there are some other energies that you should not be considering. Like for example, if I talk about electrons are moving. So inside that there is some kinetic energy also. So what is internal energy? So please write the sum of all forms of energy stored within a substance. And as of now, we will be considering only systems. Okay, within a system is called its internal energy. Is called its internal energy. Okay, so U is equal to all kind of energy which it has. E kin, kinetic energy. E part, potential energy. E rot, rotational energy. What else you can have? E trans, translational energy, and E wib, vibrational energy. Okay, so this is what the internal energy. So it is the sum of all forms of energy which is stored within a substance. Okay, which is stored within a substance. Done?
Yes, sir.
Okay. Acha, let us now imagine the same iron block. Please don't write this. And let us say it has some energy, and let us call this as U initial. And then we let it interact with the surrounding. And while interacting with the surrounding, what we are doing, we are heating it. Okay, so it is absorbing heat, and then it will get to the U final. Okay, there will be some change in energy. I don't know whether it will be increase or decrease. You will tell me that. If I heat something, then what do you think? The energy will increase within the body or it will decrease within the body? What will happen if you heat it? Arey bhai, why you guys are silent right now? Huh?
Increase. It increases.
Increase, na? Okay. Decreases or increases, Mariam? Mariam, did you say decrease?
Increases.
Increases, na? Okay, okay. Increases. Yes, so if you heat a system, the energy will increase. And it doesn't matter whether whether we are heating this with some flame or we are heating with this some let us say iron rod. We have some hot iron rod and we have just stick it to our iron block here. So it doesn't matter how we are heating it. If it is achieving this U final, it will be same if we are using flame or if we are using some iron rod. Okay, so it means that internal energy is what? It is a state function. It only depends on the state which it is present in. It doesn't matter how we have achieved that state. So right, internal energy U is a state function. U is a state function. Now, I hope you can understand it will be very difficult for us to calculate all these kind of energies which is stored within a system, right? Because we have to calculate the kinetic energy, potential energy, rotational translation energy of each and every atom which is present in the system. So rather what we say that we are not interested in the absolute internal energy. We are not interested in the absolute internal energy. Please name. We are not interested in the absolute internal energy of a system. Okay, we are not interested in the absolute energy. Okay, then what we are interested in? We are just interested in the change. We are just interested in the change. That means we are interested in delta U. Now, how will we calculate delta U? What is the formula? What will be the formula? Guess now. Mariam, delta U will be?
Delta U by U.
Delta U by U. ऐसा क्यों लग रहा है कि आपको पता है, आप कुछ बता रहे? हाँ, टेल मी, मरियम. UF minus UI.
Yeah.
And we have been, I hope you have been learning change like this only in physics. Final minus initial, right? Yes or no?
Yes, sir.
Okay. But don't you think this is very paradoxical? We just said that we are not interested in the absolute internal energy, and what we are doing here, we are just saying that we need to calculate the internal energy at the final stage. We need to calculate the internal energy at initial stage, and only we will be able to calculate the change in internal energy. Okay, so okay, can you see that this is paradoxical? Yes or no? Tell me that first. An oxymoron, a paradox. If you are interested in literature, you would know these words. No, Samaira? It is contradictory, na? This statement here, and how we have telling that we will calculate the delta U. Samaira, tell me. No.
Yes, sir.
Yes, you understand it, or you're just agreeing with me? Sometimes I feel like you're just agreeing with me in this chapter. You understand it, right, Samaira?
Yes, sir.
Okay, fine. So please, whenever you see something happening like this, please ask the teacher, sir, wait a second. What are we doing here? Why you are saying delta U is equal to U final minus U initial? You just said that you are not interested in the absolute internal energy of any system, whether it is in the final state or in the initial state. Then why you are doing this? So the teacher should answer you, no, we are not. This is not a formula. This is not a formula. Okay, please remember, this is not a formula. Not a formula. We are not going to use this to determine anything. We are not going to use this to calculate delta U. This is a definition. This is the definition of delta U. That delta U is what? U final minus U initial. Okay. So you understand what is this? This is not a formula. Okay. So whenever you are going to memorize, whenever you are going to study the formulas for delta U, this should not be in your list. Got it? Yes or no?
Sir.
Okay, this should not be in your list. Okay. Now, in chemistry, our final and initial stages are what? In chemistry, we have these type of we have something now, and we in the middle there is arrow. In the right side there are something. In the left side there are something.
Order.
What do we call those things? Reactants and products, right? Yes or no? So in chemistry, we can also define delta U as the internal energy of the products minus the internal energy of the reactants. Got it? Now there are a few things that you can write here. If, let us say, for example, if you have the internal energy of product is greater than the internal energy of reactants, then we will say that delta U is positive. Okay, delta U is positive. And if you have internal energy of products which is less than internal energy of reactants, then we will say that delta U in this case is what? In this case, it is negative. Okay. Done, all of you? Let me know if you're done.
Done, sir.
What about others? Okay, now I want to all of you to think about. Okay, so when I said now we are not interested in this change, let me go here back again. Can I say that U final minus U initial will be equal to the heat given? Yes or no? All of you agree with this? Whatever change is happening, it is happening due to this heat. So I can say that the amount of heat we are providing to the system will be equal to the change in the energy of the system. Yes or no? Yes. Okay. So again, we saw this concept, we saw this thing in thermodynamic equilibrium, and in the while we were defining the process, that we are interested in what? We are interested in the interaction between the surrounding and the system, right? So here, how are we going to calculate delta U? We are going to calculate delta U by looking at the interaction which is happening, between the system and the surrounding. Now, I will give you a situation. Let us say we have state 1. Please don't write this. And I have to convert the state 1 to state 2. And here we have, let us say 10 degrees Celsius. And here we have, let us say 50 degrees Celsius. Okay. So how can we go from a state which has 10 degrees Celsius and which have 50 degrees Celsius? You can send the answers in chat. What will you do? What should be the process here? What should we, kya karna chahiye hame? If you have to increase the temperature, then what you should be doing? Okay. Think of one another. Okay. Yeah. Okay, I got it. Think of one more way. Of increasing the temperature. Think one more way of increasing the temperature, and I will give you a hint, and that hint is maybe try to think think of a gas and think how can you increase the temperature in gas. You have your gas loss, and from there you can, I hope you can tell me a way in which we can increase the temperature. Think about the parameters which are there. Yes, Samira is giving me the right answer. Okay. Okay, fine. All of you think about, first of all of you think about all of you. No. It will be having the same number of molecules, Mariam. Okay. Think about the parameters that you have and which of those parameters is directly or it has any relationship with the temperature. Think in those terms. Think in those terms. Samira, very good. Okay, you got the answer. Bingo. Correct, Mariam. Very good. Heshma, what about you? Yes, Sarah, very good. See, all of you are saying, now all of you understand that there are only two ways in which we can change the state of systems, in which we can change the internal energy of a system, right? Hishma, Aisha. Hishma, are you there?
Yes, sir.
Can you think of the parameters? Think first of all, what are the parameters? Tell me. Aisha, you can also say, what are the parameters? Hishma and Aisha. You don't know parameters for a gas? There are four, na?
Pressure,
Pressure.
volume, temperature, and number of moles.
Number of moles. Okay. So see, we are not going to do anything with the number of moles. Okay. We are not going to do anything with the number of moles. Now tell me, what can you do to increase the temperature? What will you change? What are you going to change? What are you going to change?
Pressure.
Yeah. Okay. Now, I think all of you, please tell me yes or no. Mariam, Hishma, Aisha, Samaira, and Sarah. A change in pressure will be accompanied by a change in volume also. Yes or no? A change in pressure will be accompanied by a change in volume also. If you can't, then think about the sandbag example that you have written and see there also the pressure is changing. And I hope you can see that the volume is also changing. Yes or no?
Yes, sir.
All of you got it?
Yes, sir.
Okay, very good. Now, so please don't write any of these parts. Okay, we will be doing all the derivations and all. But see, this is the answer that you have given. I'm very glad that you all gave the answer. Okay, you all gave the answer. You're thinking in the right direction. Very good. Now, what is pressure? Pressure is what? Pressure is force upon area, right? Force upon area. Okay, pressure is force upon area. And if I am changing the pressure, there is some change in volume also. If I have, let us say, a box like this, and it is cylindrical, okay, it is cylindrical. It has a cross-sectional area of A. It is a piston like this. And if we are increasing the pressure by putting pressure, external pressure here, and that is why it will be going down. And if it is going down, then it will be having less volume. If it is having less volume, then the pressure will increase. And in that way, what we are doing, we are increasing the pressure. Okay, so basically we are decreasing the volume. So let us say it moved from here to here. So it was distance L. Okay. Now, this is the change in the volume. This is the change in the volume. Everyone following me till here? Yes or no? There was a gas cylinder here. It was having a movable piston. I added some pressure. It moved L distance from here to here. This piston was also of a ring shape and the area of cross section was A. Are you guys following me? Yes or no?
Yes,
sir.
Okay, fine. Now, can I say the change in the volume will be equal to the cross sectional area into the length? Tell me, does this make sense right now? Or do I need to revise your mathematics a bit? Should I revise your mathematics a bit? Okay, I think so. I should revise your mathematics a bit. What is the volume of a cube? What is the volume of a cube? अरे भाई इतना भी mathematics नहीं revise करवाइए हमसे please. Thank you very much. It is what? A cube. Volume is equal to A cube. Okay. Now you can see this in a different way also. Now this shaded region, what is the area of this shaded region? If this is having A and A height, this is A square, right? Yes or no? The shaded region. Are you high enough?
Yes, sir.
Okay. And if I just multiply this A, which is the area of the base into height. So you have a formula, area of base into H is equal to the volume. I hope you have seen this thing in class 10th. Even in 8th, I would say. No? नहीं देखा आप लोगों ने 10th में भी बायो था क्या आप लोगों के पास? हाँ guys, you have seen this, na? Area of base into height is equal to volume.
Yes, sir.
Okay. So now you understand why the change in volume will be equal to the cross-sectional area of the piston into the length, yes or no?
Yes, sir.
Yes, very good. Now this is delta V, which is equal to A into L, A into L. Okay. Now if I have force, and let me multiply this by this distance which is changing, L. Now I have a very good formula for work. I have a very good formula for work, right? Why I'm using work? Because I want, okay. What I want to do, I want to carry out this particular change here, which is happening. And I want to write this in terms of energy, okay? I want to write this in terms of energy. And I know that work also has the units of energy, which is in joules. That is why I'm writing the whole change in this way. Now for force, what I can do, I can just write the pressure into the area. So this will be pressure into the area and into the length, which will be equal to work. And as you can see, this will be equal to what? P into delta V, okay? So we will go into the detail of the derivation later on. But right now, I mean, just now, you have a bit of idea what these things are. So I can move on and I can write. So whatever you are doing with changing pressure, you are basically doing some work on the system, right? You're doing some work on the system. So hence we can write the next topic, which is modes of transfer of energy. Modes of transfer of energy, okay? The number one is heat, which is represented by Q. And if you have a system, and you give the system some heat, then what will happen? The internal energy will increase. And if you have a system, and if the system is giving out heat to the surrounding, I hope you understand the arrows, okay? I'm not writing these parts. I'm just diagrammatically and visually representing it. If the system is giving out heat, if it is giving out heat, then what will happen? The internal energy will decrease. The internal energy will decrease. Fine. So if you have only heat which is taking place, if you have only heat, then I will say that you are giving heat in the system. You are giving heat in the system. That means the system's energy is increasing, and hence delta U will be equal to positive, because the system's energy is increasing from initial to final. The final has more energy than initial. That is, delta U is equal to positive. And hence, whatever changes happen, we say it is due to the interaction, and that interaction has only Q. And hence, I can say Q is positive. Q is positive if we are giving it to the system. And let me differentiate here. Here, the U will be negative because it is decreasing. And here also delta U, it is equal to Q. But in this case, I can say the Q is what? It is negative. So these are what we see as sign conventions, but these are not sign conventions. These are just pure and simple logic. Okay. Can you understand these three equations? Yes or no? Maybe not, then please try to spend a bit of time while writing it, and then let me know if you can't understand these three equations. Okay. Let me know if you're done.
Done, sir.
All of you? Okay, all of you understand these three equations, yes or no?
Yes, sir.
Okay. Then the next one is work. If you do work on a system, then also what you will be doing, you will be changing the state of a system. So work is denoted by W, and you can have a system. And if you do work on system, this is what doing work on the system, then the internal energy will increase as we have done. And if the system is doing work on the surrounding, system can also do work on the surrounding. How? If you have again the same piston here, and the P external here is, and here there is P internal. So if P internal is greater than P external, then what will happen? The gas inside it will push the piston. While pushing the piston, it is doing work. Okay. So both the system can do work on the surrounding, and the surrounding can do work on the system, but it will change and it will affect the internal energy in different ways. So for example, if you have the work which is done on system, the internal energy increases. If the work is done by the system, the internal energy decreases. Okay. Please write this down. Let me know if you're done.
Done, sir.
Everyone done?
Yes, sir.
Okay. Now let us write a point regarding heat. Okay. Please write energy change. Energy change between the system. Okay, sorry, wait a second. Right, energy exchange between the system. Energy exchanged, not by, rather between the system and surrounding. Between system and surrounding as heat is exchanged between the system and surrounding as heat if they have different temperature. If they have different temperature. Now, how does the heat flow? If you have different temperature, heat flows from a body of higher temperature to lower temperature. Let me know if you're done.
Done, sir.
Done. Okay. Now, if I say for a process with no change in volume, for a process with no change in volume, del V is equal to 0. Therefore, the work done will also be 0, and hence I can say that the delta U will be only equal to Q. Okay, delta U will only be equal to Q. Okay, I missed one point.
Sir, delta V equals to Q delta U.
Delta U. This is delta U. Write a note. I missed this point earlier. But you know this, right? If you have the only changes in a system, the internal energy in a system can be changed only by heat or work. So delta U is what? Whatever heat is exchanged between the system and whatever work is done by the system or on the system, right? So this is delta U is equal to Q plus W. And this is what we call as first law of thermodynamics. Now this explains the conservation of energy. Okay. The above equation is mathematical representation of the first law of thermodynamics. The first law of thermodynamics. It explains the conservation of energy.
Done, sir.
Now let us write about work. This will be a bit elaborative. Work and W. Now initially we have seen that we will be considering the pressure volume work. Okay, so one of the work that can be mechanical work, that can be electrical work, but in this class we will be considering what? The pressure volume work. Okay, so please write the pressure volume work. Pressure volume work. Okay, so for the derivation of pressure volume work, we will take a, okay, I have to take a cylinder actually. Okay, and in this you have a movable piston. And the cylinder is filled with gas. The cylinder is filled with gas. So there are two pressure which are acting. There is P internal, and then there is P external. There is P internal, and then there is P internal, and then there is P external. Now at equilibrium, I would say, if nothing is happening, it means that P external and P internal are equal. All of you agree with this? Yes or no? This is the case where nothing happens. That is equilibrium. Agreed? Yes or no, guys?
Yes, sir.
Now, if P external is greater than P internal, then the piston will move up or down?
Down.
Down. So the work will be done on the system or by the system?
On the system.
Very good. Work done on the system. And after that, you will have P internal is greater than P external, then work is done by the system. Now let us take a case in which P external is greater than P internal. The piston moves the piston moves a distance L. Okay. Now in this time, what we are doing, we are taking the case in which we are pouring all the sand down. Okay, all the sand on the piston. We are not doing it step by step with one bean at a time. So what we will take this is a irreversible process. Okay, this is a irreversible process in which the piston is moving. Now after that, after this case, we will take the case where there is reversible process. Okay, so P external is greater than P internal. The piston moves a distance L, and piston has a cross-sectional area you have seen this symbol, yes or no? Tell me. Integration.
Yes, sir.
Okay, fine. I don't want to be that guy who introduces the integration for the first time to you. Okay, because I'm not a mathematics teacher. I just use some maths to do the chemistry and measure things. Okay, so the piston is moving what? A distance L, and piston has a cross-sectional area of what? Cross-sectional area of A. And then what I can say is the volume change, therefore, the volume change will be equal to A times L, that is delta V is equal to A times L. Now, we also know that pressure is equal to force into area. The pressure is equal to force into area. So the force will be equal to, हाँ आप लोग तो कुछ सही भी नहीं कराते हमसे, force upon area. So the force will be equal to pressure into area. What should I do next? I should write the formula for work. Work is equal to force into distance. So what is the force? The force is pressure into area. This is force. And the distance is what? It is, the distance is L. The distance is L. Okay. Now I need something from your physics. You guys know the direction. Like the force is, if I talk about force, it is a vector quantity, right? Yes or no?
Yes, sir.
Okay. Now, can you tell me what is happening if I am lifting a piece of rock up? If I am lifting a piece of rock up, then what will be the sign of work done?
Negative.
Okay, that's good. And what do you think the sign of work done will be here? So this is the P external. And this P external is what? It is opposing a force which is P internal. Yes or no?
Yes.
And the direction of the change in direction is also the same way as it was in gravitation. If I am lifting the rock up, that is why here also the work done will be negative. Okay, the work done will be negative, and I will show this as, now I am, now this was P till here, but I am writing this as now P external into the delta V, and hence what I have to do, I have to add a negative sign. Okay, I have to add a negative sign, and then this will be equal to minus P external delta V. This is work. This is work. Okay, that means you don't have to do anything else. You just have to measure the pressure, and you have to just keep in track the volume change, and you are doing what? You are determining the work. And while you are determining the work, what you are doing, you're also determining the change in internal energy, right? Because at this point of time, when there is no heat, if you have an adiabatic wall, if there is no exchange of heat between the system and the surrounding, that means the change in internal energy will only and only be equal to the work done. Okay, please write till here. Done, guys? Okay, now let us take this expression here and let us see if piston moves up and moves down, then what are the signs of work done? Let us say if you have W is equal to minus of P external del V. So there can be two cases here. In one case, the V final is greater than V initial, right? V final is greater than V initial. That means what is happening? Delta V is equal to positive. If delta V is positive, then the work done will be equal to negative, right? So here work is done by the system. And if you have the V final, which is less than V initial, here the delta V will be equal to negative, and the whole work will be equal to positive. And here I will say work done on the system.
Done, sir.
Done. Okay. Now let us write reversible work. Now we are going to take the case where you have the bag of sand and we are adding 1 grain at a time. We're adding 1 grain at a time. Now, if I add 1 grain at a time, the displacement of piston will be, I can say displacement of piston. Can I say it will be equal to dl, a very small distance? Yes or no? Huh, guys?
Yes.
Yeah, okay. Now this will be accompanied by a change in volume. So if I am moving a very little distance, then the change in volume will be significant or it will be very little? It will also be little, right? The change in volume. For example, if you have this piston here and it is just going from here to here. So again, I can say that the change in volume, it will be equal to what? A times dl, correct? Any doubt, guys? Till here, any doubt? No doubt now?
No, sir.
Okay. Now we have the same expression for pressure, which is equal to force upon area. And we have the same definition for force, which is equal to pressure into area. However, the work which will be done by this, the work which will be done on the system right now, if the piston is moving a bit down, it will be very small work. So I will say this is dW, which will be equal to the force into the distance. And this force is nothing, but it is P into A, and the distance is dl, and hence the dW, this will be equal to the pressure, that is external pressure, into ADL, and ADL is nothing but it is dV. And I have to add a minus sign here, right? I have to add a minus sign here. Now what should we do? We should integrate both sides. Integrate both sides. So here you will get what? Integration of W is equal to the integration of minus of P external dV, minus of P external dV. And this particular work, which I will see now, it will be what? This is the reversible work. Okay, the reversible work, which will be equal to minus of P external, and integrating the dV, because you have only dV term, from initial to final. It is going from initial to final, and this will be equal to minus of Px. In square brackets, we will have y. We will have the volume, the V initial to V final, and this will be equal to again minus of Pex into V final minus V initial. And we are back on the same formula, which is equal to minus of P external delta V. This is what? The work done in a reversible manner. The work done in a reversible manner. Done?
Yes, sir.
Okay. Now let us look at this particular work done in terms of the P internal, because we are doing what? We are focusing on the system. We will be doing all the measurements on the system. We are not focused on the surrounding, right? So now this P external is what it is, telling me everything in terms of what? The surrounding. No, I don't want anything in the terms of surrounding. That means I have to convert this particular equation such that I have P internal in it. That means I have to look at this P external as P internal. Okay, so let me see. Let me write in terms of P internal. Okay, now suppose you have a piston here, the same thing, and there is one sand which is added here. then this piston will move a bit down. This piston will move a bit down. And if it is moving down, then the volume will decrease of the system. Yes or no? The volume will decrease. Yes or no? The volume will decrease, no? If the
Yes,
volume is
yes.
decreasing, that means the internal pressure will increase little. It will increase by a little amount.
Yes, sir.
That means I can say the P external now it is equal to the P internal plus dP plus dP. Okay, plus dP. And after adding 1 grain, what will be there? You can't see any change. That means you will say now it is again in equilibrium. That means the P external and P internal plus dP is now equal until and unless I add another sand. And then again I add another grain of sand. Okay, so P external is equal to P internal plus dP. We had dW. So we will take the equation from here. We're going to take this equation from here and we will write the dW. It is equal to the integration of dW is equal to the integration of minus P external, not delta V, rather it is dV. Okay, now I can write that this is the reversible, and rather than writing P external, I can write this. Let us take this minus sign away, and I will write P internal plus dP into dV, and I can see minus of integration of P internal into dV plus the integration of this is again whole in bracket plus the integration of dP dV. Okay, now as you know, since dP and dV both are very small, it will be negligible, are very small, correct? So this will be negligible. So if you have, for example, 0.0001 and you have 0.000001, if you multiply both these small terms now, the result, the product will be again very small. Okay, it will be very small. That is why you can say I can neglect this term. Okay, so I'm neglecting this term. And you will be just remaining with the negative of integration of P internal into dV. Now, all of you know that I can write the P internal and applying the ideal gas equation. So P will be equal to nRT upon V. nRT upon V, and hence I can write minus of integration of nRT upon V dV, which will be equal to, again, nRTs, these can be gotten here, integration of 1 upon V dV. So 1 upon V is ln V. I have to add V final, let us say V1, V2, whatever the change is there. So again, this is what V reversible. It will be equal to minus nRT. 1 upon V is ln V from V1 to V2 minus nRT ln V2 minus ln V1, and this will be equal to minus of nRT ln V2 upon V1. Okay. Those who know some logarithms, they can say that this will be equal to minus of 2.303 nRT log of V2 upon V1. Now I will write one more term here. You have to figure it out, okay? Minus 2.303 nRT log P1 by P2. You know the relationship, right? P1 V1 is equal to P2 V2, correct? And that is why I can say V2 upon V1 is equal to P1 upon P2. Let me know if you have any doubt till here.
Sir, we have integration in the numericals as well.
No. This is just a derivation. Why I am doing the derivation? Because this is in your second term. Your second term is subjective or objective?
Subjective.
Subjective. Otherwise, if it was objective, I would not have asked you to write this derivation. I would have done this derivation, but I would have asked you to just see this derivation of how it is happening. Okay, how many of you are using a laptop here?
No, sir.
You are using a
Sir.
laptop. Aisha is using a laptop. What about?
Yeah.
Okay. Hishma, you are not using a laptop?
No, sir.
Hishma, do you have any friends here? No.
No,
No, you don't have any friends also. Okay, so no, I can do one thing. I have to actually share. How many of you are comfortable with logs now? Dealing with logs? No one is. I know logs are a bit difficult. So I'm sending this to everyone. You will see a PDF, and what I can do for Ishma is that I can give her a link from there she can download the thing. Okay, so I forgot which website this was.
sir, should I log in from the laptop?
If you can, then it will be good. But I mean, if there is some difficulty, and I think you will leave now for prayer, no?
Yes, sir.
So just wait a second. Let me give you the link. From here, you can download it, okay? And I'm sharing this link for everyone. If you want it, you can download all of you. Okay. Did you get this, Hishma?
Yes, sir.
Can you click on it? Now, this is 5-page, okay? Now, this is a very sincere advice. And this advice is coming from someone who got comfortable with logarithms only in his bachelor's. In this particular 5 pages, it helped me a lot. What you need to do is shut the door of your room, sit with these 5 pages. Maybe if you can print this out and do the complete thing, no matter if it is taking 1 hour, 2 hours, or 3 hours, just do the complete thing. You read each and every point, do all the problems in the exercise which it has. It does not have very much if you get the idea what is happening in logarithms, but this is the only way for learning, okay? Logarithms. No matter how much a teacher is going to teach you, until and unless you spend time on logarithm, and it is only once. There are some subjects now which you have to read daily, like half an hour daily. If you read it, then it will be okay. But there are some other subjects, some other topics which you have to do in one sitting. Logarithm is one of those things. So please make a slot in this week only, okay? Because you will be dealing with logarithms in thermodynamics. This applies for also those who have mathematics, because in math, I know you don't have to deal with log so much. You have to only deal with the properties of log. Hannah? Am I right? Or no, you have to deal with logs also? Though you have to calculate the values? No, yes, nothing. कुछ बोल ही नहीं रहे हैं ये लोग. क्या हो गया आप लोगों को? Yes, Shishma, first tell me, did you download the PDF? Yes or no?
Yes, sir, I did.
Okay, fine. You can go for prayer. What about others? Done?
Yes.
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 Okay. Now, we have already seen the law of conservation of energy and the first law of thermodynamics. Now, let us just write the topic, and it should be in your page, right? Should be in your notes. Then how much time do I have? Should I do some numericals? Okay, let us write. Law of conservation of energy, है ना? first law of thermodynamics. First law of thermodynamics. What does it state? It states that energy can neither be created. Energy can neither be created nor destroyed. Although it can be converted from one form to another. From one form to another. Okay. Now there are some points. The first point is the total energy of universe is always constant, or I should say it remains constant. Universe remains constant because whatever the transfer of energy is happening, it is happening inside the universe, and that is why the total energy of the universe, it will be constant. Next is the energy of isolated system. The energy of isolated system is what? It's always constant. Then
Yes, sir.
you can write. If we talk about systems, now if we talk about systems, then I can say change in internal energy. Change in internal energy. This will always be equal to, the heat added to the system plus work done on the system. Okay. So if you want to increase the temperature, if you want to change the internal energy of a system, it can be done only in two ways. That is either by heat or work. We have done this previously also. This is Q plus W. Then
That's
okay. Now see, I hope you can do the sign convention. Let me. So this is the equation. Okay, this is the equation, and this is when you have heat is added to the system. So heat is positive. Work is done on the system. So work is positive. Okay, but if you have a case where heat added to system and work done by system, then the delta U, it will be equal to heat added on the system, so it will be positive. Work is done by the system, so hence the work will be negative, and then the delta U will change to Q minus W. Okay, so I hope you don't get worried by these type of things. Yes or no? And hence you can say also what delta U, and you have seen, is equal to Q minus what is W? W is what is W? W is
Work done
Work done. Okay, what is the formula for W? You have just seen a pressure volume work.
DP.
DP नहीं, अभी तो निकाला ना. We have done just now this all things. P delta V, P into minus P del V, minus P del V. Okay, got it?
Yes, sir.
Okay. So you have to remember, okay, I hope you can do the sign convention. You will not get confused with the sign conventions, right? If it is work done by the system, then it is negative. Work done on the system, then the W is positive only. So just remember these two, which are important. Delta U is equal to Q plus W. And you can change the signs. If this work is done on system or by the system, or heat is given by the system, or if heat is added to the system. And you can also write Q plus minus of P external into delta V. This is another equation. This is another equation by which we calculate the change in internal energy. So this equation is important. Q minus P external into delta V. This is more important. Okay. Why this is more important? Because see, क्या work done आप लोग calculate कर पाइएगा ऐसे? Like if you are seeing something happening, you cannot ना. You can, but you can determine the change in volume while you are looking at a system. So that is why this is more important. Whatever you can see and whatever you can feel, it is more important. Okay. So this equation is more important. Whenever you are going to use, then you are going to use this equation. Don't forget this equation. What I mean is that don't forget this equation. Q minus P into delta V. So this is pressure volume work. Okay, this is pressure volume work. Please don't forget it. Just do a few questions, then. Then guys.
Done, sir.
Okay. Now let us take a case. Okay, now let us take a case. Case where we will have different types of internal energy change. Okay, internal energy change. Let us suppose if you have a system in which the process is of constant volume. Okay, so delta U for isochoric. Okay, so what is delta U? Delta U is equal to Q minus
P delta V.
P external into delta V. Okay, so isochoric process means what? What is constant? Look in your notes and tell me isochoric process, what is constant?
Volume.
Volume is constant. That means delta V will be equal to 0. Yes or no? Delta V will be equal to 0 now, because this is V final minus V initial. V final and initial are same since it is not changing. That is why Q minus P external into 0. So delta U will only be equal to what? The heat exchange. So these are some results. Okay, you have to remember these results. You have to commit them to the memory. Okay, done. For isochoric,
None, sir.
now if you have let us say delta U for process with no heat exchange and constant volume. Okay, there is no heat exchange and there is also constant volume. Then the delta U will be equal to what? Q minus P external delta V, P external delta V, and this will be equal to Q minus, so this is Q is 0 because there is no heat exchange. The Q is 0 minus P external into 0, which will be equal to 0. This is another result that you have to remember. The change in internal energy for a process with no heat exchange and constant volume will be equal to 0. Okay. Done?
Done, sir.
Okay. Let us do one question. Okay, let us do one question. Right? A gas absorbs a gas absorbs 120 joule of heat. Okay, okay. Now what will happen if it is absorbing heat? The volume will increase or decrease? The volume will increase or decrease? Properly, थोड़ा ठीक से बोलिए ना, आप लोग ऐसे क्यों बोलते हैं? Yes, Mariam?
It will increase.
नहीं, ठीक से बोलिए. How do I say like this? Gas absorbs 120 joule of heat, expands against external pressure. I don't say it like that, na? Yes, Mariam.
It will increase.
Thank you very much. It will increase. Okay. A gas absorbs 120 joule of heat and it will expand, right? And it expands. Now, if it is expanding, there is always some external pressure which will be there. Okay. If it is expanding, there will be some external pressure, right? And expands against the external pressure of 1.10 atm. 1.10 atm from a volume of 0.5 liter to 2 liters to 2 liter. What is the change? What is the change in internal energy? Okay, so we will solve this, but ऐसे नहीं कि like we will add this formula and then in that formula we will insert whatever we seem it is given in the question. So okay, so we will not do that. We will not do that. What we will do, we will imagine a system like this. We'll imagine a piston like this, right? And I will say the external pressure is 1.10 atm, and I am doing what? I am heating this. Okay, I am heating this. Now tell me, if I am heating this, if it is expanding, then the piston moves up or down? Piston moves up or down, tell me. Piston will move up or down if it is getting heated. If it is expanding,
It will move up.
piston moves up. So tell me, now the system is doing work, yes or no? Because system is the one which is lifting the piston up, na? System is doing work?
Yes.
Yes, sir.
Yes, okay. So work done by system. Now, if system is doing work, then the sign for that work will be what? It will be negative, na? Yes or no? So then W will be equal to what? First of all, let us calculate the W. W will be equal to minus of P delta V. This will be always the formula, okay, for work. It is not because the work is done by system here, okay. So tell me, what is the pressure here? Minus of 1.10. Delta V is what? final minus initial, right? Delta V is final minus initial. What is the delta V? 2 liters minus 0.5 liters. So this will be equal to 1.10 into 1.5. No? Yeah, 1.5. Whatever the answer will be, it will be in joules. Please calculate it now. The units here are liter ATM. Okay, I will give the conversion factor. First do it. Okay, Sarah got the answer 1.65. Yeah, this is minus 1.65 liter ATM. Okay, liter ATM. Just write here 1 liter ATM is equal to 1 point, so not 1.1, not 1.101.3 joules. Okay, it is equal to 1.101.3 joules. So I can say it will be somewhere around 167. Okay, if I multiply, yeah, it is somewhere around 1.67. I can say minus 167 joules. Minus 167 joules. Okay, so this is your work, and you can see it is a negative, right? It is a negative because it was done by the system, and if it was done by the system, the volume will increase. If the volume will increase, the delta V will be positive, and hence the work will be negative. Okay, the work is negative here. And what we have seen, the heat is absorbed by the system. Heat absorbed by system. That means it will be in positive value. So I have to give what? 120 plus 120 joules. So delta U is, we have the ultimate formula, that is Q plus W. And W is taking care of itself, right? It is 120 joules. Now W is what? It is minus 167 joules. So delta U will be equal to what? Will be equal to minus 47. No, minus 47. Yeah, minus 47 joules. Minus 47 joules. Write this down. Let me know if you're done.
Done, sir.
Okay. Now, right. What is the work done? Work done if gas expands without any external pressure. That means it does not have any force which is opposing it. Without any external pressure. Okay, so let us see. First of all, please listen. Let us look at the formula. We will look at the formula minus Px del V. Now, if we have The P external is what? Without any P external, that is why the P external is what? P external is equal to 0, and hence the work will be 0. Yes or no? The work will be 0. Okay. Now tell me, please tell me. If you are pulling, if you don't, if you're not applying, if there is no opposing force, if there is no gravity, then there is no work done, na? While lifting something. If you are lifting something, we are doing work against the pull of gravity. Only then we say there is some work done. But if there was no gravity, that means we were lifting something up. We are not doing any work, right? And this is what we mean if it expands without any external pressure. Okay. So to work is done, then there should be some external pressure. Now this type of expansion, it is known as free expansion. Expansion of gas at P external is equal to 0 is called free expansion. Okay, so these are the things that you have to remember. Okay, these are the things that you have to remember. So let me know if you have done this, then we can end this session. You will get some simple assignment. Please do it. Okay, please check your website or the app, whatever you have logged in. You will get 3 questions. Okay, simple. Do those, then we will meet on Wednesday. Hey, tomorrow we will meet tomorrow, na? Huh?
Wednesday.
Wednesday. क्यों? कल
The
आपकी होती है ना?
term 2 classes next will be
Term
on
2,
Wednesday.
yes. Term 2 on Wednesday, but term 1 we will meet tomorrow. Okay, done, guys.